Welcome back to Reconstructing Gravity. This is Ted Cole again in chapter G15 called Internal Harmony. In this video, I'm going to present a significant conceptual breakthrough regarding the physical source of gravity. In earlier gravity videos, I showed that a variety of gravity problems can be solved by assuming that space moves towards planets at the escape velocity of the planet, and that to achieve this velocity of space, the flow rate of space outside a planet must diminish at a constant rate. Dflow rate dt equals 12 pi gm, where m is the mass of the planet. In my last video, G14, we looked at the flow rate inside a planet, finding that there were two components to this. That dflow rate dt had one term that was 12 pi gmi, that's the mass inside some internal radius r, and another term which is 48 pi r over the density of the planet times the internal pressure. This suggested that internal pressure plays an important role in the physical cause of gravity. Now, the conceptual breakthrough which I'm going to present here came from returning to some ideas I presented earlier about the behavior of non-accelerating masses that exist in a gravitational field. In my video G6, I talked about the concept of a strain gradient balancing the gamma gradient, which is caused by the downward acceleration of space, such that a mass in a gravitational field can maintain its internal harmony of energy cycling. The basic idea is that energy cycles harmoniously inside every particle of mass. But in a gravitational field where the space is accelerating downwards, there's a higher space velocity in the lower part of the particle than the upper part of the particle. And this causes the cycle time to be longer in the lower part of the particle, which makes the return point not at the same central point, but a little bit lower. And over repeated cycles, this causes that mass in a gravitational field to accelerate downwards, to drop. The corollary is that in order for a mass particle to not drop when it's in an acceleration field, there needs to be some force underneath which causes a strain gradient. In other words, the lower half of the particle must be compressed more than the upper part of the particle, such that the energy does return to its initial starting point when it's cycling. This strain gradient within a mass is created by a pressure gradient within a mass, which is supported by an upward force in a gravitational field. Now, 2 points are relevant here. First, the entire planet is composed of mass particles that exist in a gravitational field. But unlike the first time we looked at this problem, where we're just looking at a small chunk of matter that was at the surface of the planet, when we look at the whole planet, gravity changes as a function of the internal radius of the planet. The pressure changes, the strain will change, the space velocity changes, and therefore the gamma will change. So these things are not fixed, and we want to look at the whole picture of how this fits together. Now, I just want to say that I had been looking for some internal relationship, some unifying principle for a very long time, better part of a year, I think, and looking at, pressures, the flow rate, the flow rate dt, the gamma. But when I had this idea, everything fell into place within a matter of hours. To simplify things, I was thinking in terms of megamasses. This is the same concept that was used when we looked at the ball drop in an earlier video. And at first, there's nothing new here. Just look at the mass in region A, and we say that the energy cycling inside A exists in a region of a velocity gradient because of near the surface of the Earth, the space is accelerating downwards, And so in the upper half of A, it takes a certain amount of time to cycle, for the energy to cycle back to where it started. But because the space is moving faster in the lower part of A, it would cycle more slowly. In order to get the upper and lower energy cycles to return to the midpoint at the same time, there needs to be a pressure that shortens the lower part of region A. An analogy that might help here is, suppose you had two runners starting at the same point but running in opposite directions and then returning to the same place. But they're running through wind, and wind slows down their time of cycling. Now, the wind helps you somewhat when you're going downwind, but it hurts you more when you're going upwind, so that the higher the wind, it still makes the cycle time slower for running a round trip. So in order for the two runners to return to the starting point at the same time, the track for the runner that's in the higher wind area needs to be made a little bit shorter. So that's an analogy for what's happening here. The energy cycling inside each particle needs to return at the same time. But in order for that to happen, the lower part of the particle needs to be compressed to shorten the distance so that the return time is equal. Now, the new idea here is realizing that the lower part of mass region A is the same as the upper part of mass region B. So B exists in a different velocity gradient region, but B has the same situation. It's not accelerating downward, it's not falling. So it also needs to have its cycle times be equal in the upper and lower portions. So B needs to be, because it has even higher velocity gradient, B needs to have an even higher pressure in order to make its cycle times equal, so that the energy returns at the same time in both halves of B. But then again, we look at the relationship of region B to region C. The lower part of region B is the same as the upper region of C. So again, C will need even more pressure to keep its cycle time the same in the upper and lower regions. But the important fact here, the thing I realized, is that in all of these regions, A, B, and C, the cycle time will be equal. The cycle time in the lower half of A will be the same as the cycle time in the upper part of A. But because B has that relationship to A and B has that relationship to C, that means that the cycle time in A and in C will also be equal. And because we can extend this all the way down to the center of the Earth, that means that the cycle time in every region of mass will be equal everywhere inside the planet. That's a new idea. That's a unifying concept. Importantly, when just looking at region A, or mass near the surface of the Earth, we could fairly assume a linear gamma gradient, pressure gradient, and strain gradients over that very short radius range of a small object near the surface of the Earth. But as we go from the planet's surface all the way to the center of the planet, these gradients are very much nonlinear. With these nonlinear functions we've already computed for pressure, space velocity, and gamma, will it hold true that the energy cycle times are the same for every particle inside the planet? Is that the unifying principle? Well, that's what we're about to find out. Let me insert a quick note before proceeding. There are two types of logical reasoning. Induction, which is reasoning from observed facts to draw general conclusions, and deduction, which is reasoning from general knowledge to make specific predictions. Clearly, what we're doing so far here is primarily induction. We're looking at the observed facts. We know how gravity works. We know we can compute pressures inside the Earth. We know what G is at the surface of the Earth. And we're looking for the general conclusion, the common thread, the underlying principle. Before I show the results, let me lay out a few definitions. This epsilon is what we're going to call strain, which, as you recall from the definition before, was a change in length over the original length. And in this situation, we're going to use the strain at the surface of the Earth as our reference point, because we're saying everything inside the planet will be related to what's happening at the surface of the planet. So in that case, the strain is 1 minus the new length, the shorter length. And we're also going to assume that strain is proportional to pressure. That is generally how it works. The shortening of the material, the shortening of the particles is due to the pressure on the particle and directly proportional. So here's my table of results looking at these things. You see over at the left, R over R sub E, so it's 0 at the top. That's the center of the planet, and the outside of the planet is down at the bottom at 1. And so we see at the bottom the familiar space velocity in the third column, 11,185 meters per second is the velocity of space, and it's higher at the center of the planet, 13,699 meters per second. And so each of those velocities has a gamma associated with it. And obviously the gamma gets higher towards the center, but not in a linear way. And we present those gammas. And then to represent the strain, we look at, well, what's the difference between the strain at the bottom, or the gamma at the bottom, where we have 1, and then every gamma, every number in that column above that where it says multiplier to get common gamma. That's essentially the proportional amount of shortening. Think in terms of that racetrack. The amount of shortening, the distance shortening that would be required to have the same time event. And then the next column is pressure over density, which is just proportional to pressure, which is a function that we've already computed. And then the next column is the strain required to get that common gamma. In other words, the strain required to change the length such that the gamma is the same. And of course, at the bottom, which is the outside of the Earth, no additional strain is required. There is some strain, but this is our reference point. Our reference is the outside of the planet. So no additional strain is required at the outside, but as you go inward into the planet, as you go higher up the table, more strain is required to bring the timing into unison. And then we see that in the next column, that green column, we look at pressure over strain, and we see that, in fact, it is a constant. So that assumption that pressure over strain is a constant is true. And in fact, in the last column, we see that constant is related to the speed of light, which requires a little more analysis and thought, but it's interesting that the speed of light is right in this whole thing, because speed of light is really what defines the gammas. So you might want to stop or come back to this table to look at it after we talk about some other things. The result in the prior table showed that the ratio of pressure to strain equals the density of the planet times c squared. That's a constant. Well, if you play around with the two sides of this equation, the ratio of pressure to strain is dimensionless, and pressure can be re-expressed as energy per cubic meter. whereas the right side of the equation is density times c squared is mass density times c squared. So it comes down to energy density equals mass density times c squared, or once again, E equals mc squared. Very interesting. Here's another graphic I made for this table. The lower curve shows the L2 to balance time, which is essentially the strain relative to the strain at the outside of the planet. And that has to balance the gamma, which the gamma at the outside of the planet has to increase to balance that. So the reference point is the state of the mass at the outside edge of the planet, and has to be the gamma has to balance the strain all the way in. I'll let you think about these ideas before continuing next time, but one more quick thought before we go. In the last video, I kind of made a big issue about pressure being important, and I said that it was rarely mentioned in a lot of statements about Einstein's general relativity. They talk about mass, but not about pressure, I said. But in fact, one of Einstein's key elements in his field equations is called the stress-energy tensor. And stress is just another word for pressure. So it was right there in my face all along. Gotta laugh. Well, thanks for watching. I've got more to say, and we'll pick up on it more next time, though. This video has already been pretty long. But please like and subscribe if you would to my YouTube channel and this video. And I'll pick some music for our outro, and catch you next time.
Oh, please don't hurt my pride like her, 'cause I couldn't stand the pain, and I would be sad if our new love was in vain. So I hope you see that I will love to love you, and that she will cry when she learns